This is Basic Computer Networking for Building Automation Systems, presented by Linkspring. Background knowledge for systems integrators and building managers, and what to consider when you introduce your BAS onto the network. In this presentation, we'll talk about computer networking as it relates to building automation systems, with a specific emphasis on Genesis controllers. First, we'll talk about network types and categories. Then we'll give you a bit of introduction to the architecture. We'll discuss protocols and the equipment used on networks, and then we'll dig deeper into IP addresses, which are important in most modern building automation systems. We'll even show you how to examine the network with a few basic commands, and then how to set up a Jenny controller given what you discover. A network is any number of computers or other network-enabled devices sharing a common communication medium. We used to say that they were wired together, but now that we have wireless communication, cell phone networks, satellite relays, the wired part of the statement doesn't really quite cover all the options. As long as the computers or devices can communicate between themselves, you can consider it a network. Computers on a network can share files or devices such as common printers, external storage devices like hard drives, backup functionality, and many other things. Building automation networks can bring network-enabled building systems together so that they can work in concert. Networks can be small, as in 2 computers in a home or small office, or large, like the Internet, with hundreds of thousands of PCs and devices communicating together. A network can exist solely within the confines of an office, like a LAN or local area network. Or it can be spread out over long distances, such as satellite offices sharing files and email with the home office on the other side of the world. Companies rely heavily on networks to share resources and communicate through email. Users can communicate with and control devices on the network. Let's talk about the types of networks, and we'll start with LANs. LANs, or local area networks, are networks usually confined to a geographic area, such as a single building or a college campus. LANs can be small, linking as few as 3 computers, but they often link hundreds of computers used by thousands of people. The development of standard networking protocols and media has resulted in worldwide proliferation throughout the business and educational organizations. Wide area networking combines multiple LANs that are geographically separate. This is accomplished by connecting the different LANs using services such as dedicated leased phone lines, dial-up phone lines, both synchronous and asynchronous, satellite links, fiber optic, and other data packet carrier services. Wide area networking can be as simple as a modem and a remote access server for employees to dial into, or it can be as complex as hundreds of branch offices globally linked using special routing protocols and filters to minimize the expense of sending data over vast distances. The Internet is a system of linked networks that are worldwide in scope and facilitate data communication services such as remote login, file transfer, electronic mail, and the World Wide Web. With the rise in demand for connectivity, the Internet has become a communications highway for millions of users. With the advent of wireless technologies such as cellular modems and satellite transmission, the Internet no longer requires an office with a network to access it. The Internet is a full-fledged conduit for many forms of information and commerce. Internet websites now provide personal, educational, and economic resources to every corner of the planet. Because browser-based software is so powerful, ubiquitous, and inexpensive, many private organizations implement their own intranet. An intranet is a private network using Internet-type tools, but available only within a given organization. For large organizations, an intranet provides an easy access mode to corporate information for employees, shared calendars, office-to-office chat, private messaging, and much, much more. VPNs, or virtual private networks, use a technique known as tunneling to transfer data securely over the Internet to a remote access server on your workplace network. Once the connection's made, the user has access to most of the usual network resources such as shared hard drives and email, etc. From a building automation standpoint, one of the options for seeing and controlling building systems is a VPN connection to an on-network device or building management workstation. When someone is connected with a VPN, they can examine devices on the business network and make adjustments as needed. Let's briefly discuss the categories of networks. Networks can be divided into 2 main categories. There's peer-to-peer and server-based. In peer-to-peer networking, there's no dedicated servers or hierarchy among the computers. All the computers are equal and therefore known as peers. Normally, each computer serves as a client server, and there is no one assigned to be an administrator responsible for the entire network. Peer-to-peer networks are good choices for small organizations where the users are allocated in the same general area and security is not an issue, and the organization and network will have limited growth within the foreseeable future. Server-based networks use the term client-server to refer to the concept of sharing the work involved in processing data between the client computer and usually the more powerful server computer. The client-server network is the most efficient way to provide databases and management of applications, spreadsheets, accounting, communications, document management, network management, and centralized file storage. In the building automation world, most of the protocols can use both peer-to-peer or server-based when sharing data between the separate devices, depending on the customer's equipment and requirements. In this example, information that's sent over the LAN and BACnet protocols follows the peer-to-peer concept. The information being collected by the Genesis controllers is then served up to the AX supervisor for management using this server-based network structure. Client-server design can let the application provider mask the actual location of the application functions. The user often does not know or care where a specific operation is being executed. The entire function may be executed in either the PC or the server, or the function may be split between the two of them. For example, in most internet sites, the user requests a page, and the server creates it and sends it back. The user's own PC then displays the page on the screen. When the user clicks a link, for example, this sends another request to the server, asking it to send another page, and the process repeats. However, instead of the server doing most of the work, it's possible, and quite common, for the server to send the page along with a small program. The user's computer displays the page and loads the program, and when the user interacts with the page, the user's own computer can respond and react based on the program that the server sent. That way, the user's computer is the one running most of the processing, leaving the server to address other users and their requests. When the user's finished with the page and the program, their browser abandons and destroys it until they visit the site another time. Often, the user's not even a real person. For example, in modern building automation systems, the controller, say a controller hooked to an HVAC unit, will ask for the information from the server and will react based on those commands that the server said to do. When the operation is complete, it may send the results back to the server, who collects them for reporting purposes. The real human user can log on to either the controller or the server and interact with them, even override the server's instructions. Let's talk about some of the various architectures that networking can call into use, and we'll start with Ethernet. Ethernet is the most popular physical LAN layer technology in use today. Other LAN types include Token Ring, Fast Ethernet, Fiber Distributed Data Interface or FDDI, Asynchronous Transfer Mode, and Local Talk. An Ethernet connection is popular because it strikes a good balance between speed, cost, and ease of installation. These benefits, combined with the wide acceptance in the computer marketplace and the ability to support virtually all popular network protocols, make Ethernet an ideal networking technology for most computer users today. Ethernet is a standard. The Institute for Electrical and Electronic Engineers, or IEEE, defines the Ethernet standard as IEEE Standard 802.3. This standard defines the rules for configuring an Ethernet network, as well as specifying how elements on an Ethernet network interact with one another. By adhering to the IEEE standard, network equipment and network protocols can communicate efficiently. All kinds of devices use the Ethernet: printers, servers, PCs, and even building automation systems. And it makes sense because rather than inventing and maintaining their own proprietary standards, these devices can simply tack themselves onto an existing network and have the access to all the devices on that network. You'll see how this is important when we start talking about protocols. Token Ring is another form of network configuration which differs from Ethernet in that all messages are transferred in a unidirectional manner along the ring at all times. Data is transmitted in tokens, which are passed along the ring and viewed by each device. When a device sees a message addressed to it, then the device copies the message and then marks the message as being read. As the message makes its way along the ring, it eventually gets back to the sender, who now notes that the message was received by the intended device. The sender can then remove the message and free that token for use by others. All right, let's talk about protocols. Protocols are standards that allow computers to communicate. A protocol defines how computers identify one another on the network, the form the data should take in transit, and how this information is processed once it reaches its final destination. Protocols also define procedures for handling lost or damaged transmissions or packets. TCP/IP, IPX for Novell NetWare, AppleTalk for Macintosh computers are the main types of network protocols in use today. Building automation systems use their own protocols such as BACnet, LawnWorks, and Modbus. Although each network protocol is different, they all share the same physical cabling. This common method of accessing the physical network allows multiple protocols to peacefully coexist over the network media and allows the builder of a network to use common hardware for a variety of protocols. This concept is known as protocol independence. The important point here is that networks, once cabled together in a given architecture, can share the transmission lines that connect them and speak to each other using a predefined and standardized protocol to communicate with the relevant devices. That's why building automation systems, for example, can coexist on a network that might otherwise share printers, documents, files, and emails and do their job without affecting any of those. Let's talk about a specific and important protocol, TCP/IP. TCP stands for Transmission Control Protocol, and IP stands for Internet Protocol. The term TCP/IP is not limited to just these two protocols, however. Frequently, the term TCP/IP is used to refer to a group of protocols related to the TCP and IP protocols, such as User Datagram Protocol, or UDP, File Transfer Protocol, FTP, Terminal Emulation Protocol, Telnet, and so on. TCP/IP provides end-to-end connectivity, specifying how data should be formatted, addressed, transmitted, routed, and received at the destination. Many building automation controls can speak TCP/IP, allowing them to coexist on the business network and their traffic to be handled like any other device. The standards and technology that have just been discussed help define the specific products that network managers use to build Ethernet networks. Ethernet is by far the most popular of the network architectures in the world. The following information discusses the key products needed to build an Ethernet LAN. Network interface cards, commonly referred to as NICs, are used to connect a PC to the network. They can be wired or wireless and can be integrated into the PC, added as an option card on the PC's internal bus, or even plugged in as a USB adapter. In order for a device to have connectivity to a network, it must have a network interface card or a built-in network communications methodology. Many modern building devices contain communication capabilities that allow them to access the network. All right, let's talk about Ethernet hubs. A hub combines multiple Ethernet devices together on the same network. Hubs are similar to switches, which we'll talk about shortly. In a hub, any data packet coming from one port is sent to all other ports. It's then up to the receiving computer to decide if the packet is for it. Hubs do not try to enforce any logic or use any smart algorithms to forward the traffic. They simply take in what they're sent, amplify it, and repeat it. The biggest problem with hubs is their simplicity. Since every packet is sent out to every computer on the network, there's a lot of wasted transmission. This means that the network can easily become bogged down. Hubs are typically used on small networks, where the amount of data going across the network is never very high. The function of a bridge is to connect separate networks together. A bridge goes one step up on a hub in that it looks at the destination of the packet before it sends it. If the destination address is not on the other side of the bridge, it will not transmit the data. A bridge has only one incoming and one outgoing port. Ethernet switches are an expansion of the concept of Ethernet bridging. LAN switches can link many networks together. When a packet comes through a switch, it's read to determine which computer to send the data to. This leads to increased efficiency in that packets are not going to go to computers that do not require them. It takes more time to examine the entire packet, but it allows the switch to catch certain packet errors and to keep them from propagating through the network. Most large networks use switches rather than hubs to connect computers within the same subnet. A router is similar to a switch in that it forwards packets based on an address, but instead of the MAC address that a switch uses, a router can use the IP address. This allows the network to go across different protocols. The most common home use for routers is to share a broadband internet connection. The router has a public IP address, and that address is shared within the network. When the data comes through the router, it is forwarded to the correct computer. Routers filter out network traffic by specific protocol rather than by packet address. Routers also divide networks logically instead of physically. An IP router can divide a network into various subnets so that only traffic destined for a particular IP address can pass between the segments. Network speed often decreases due to this type of intelligent forwarding. Such filtering takes more time than that exercised in a switch or a bridge, which only looks at the Ethernet address. However, in more complex networks, overall efficiency is improved by using routers. A firewall is a system or group of systems that enforces an access control policy between two networks. The actual means by which this is accomplished varies widely, but in principle, the firewall can be thought of as a pair of mechanisms, one of which exists to block traffic and the other of which exists to permit it. Some firewalls place a greater emphasis on blocking traffic, while others emphasize permitting traffic. Probably the most important thing to remember about a firewall is that it implements an access control policy. If you don't have a good idea what kind of access you want to allow or deny, a firewall really won't help you. It's also important to recognize that the firewall's configuration, because it's a mechanism for enforcing policy, imposes that policy on everything behind it. Administrators for firewalls that manage the connectivity for a large number of hosts therefore have a very heavy responsibility. We talked about the fact that a router can communicate with other devices using the IP address instead of the MAC address. So what is an IP address and what's it used for? An IP, or Internet Protocol address, is a unique identifier for a device or a node or a host connection on an IP network. An IP address is a 32-bit binary number, usually represented as 4 decimal values, each representing 8 bits, in a range of 0 to 255. These are known as octets, separated by decimal points. For example, 173.201.146.1. Every IP address consists of 2 parts, one identifying the network and one identifying the node or device. The class of the address and the subnet mask determine which part belongs to the network address and which part belongs to the node address. Let's talk about address classes. There are 5 different address classes. You can determine which class any IP address is by examining the first 4 bits of the IP address. Class A addresses start with 1 to 126. Class B is 128 to 191. Class C is 192 to 223. Class D is 224 to 239. And Class E is 240 to 254. Now we can see how class determines by default which part of an IP address belongs to the network and which part belongs to the node. In a Class A address, the first octet is for the network address and the rest identify the node. In a Class B address, both of the first 2 octets identify the network and only the last 2 are for the node. And in Class C addresses, the first 3 octets identify the network and only the last one identifies the node. There are a few IP address classes that are reserved for one reason or another. Some of the more important ones are addresses starting with 127 dot. These are for loopback and internal testing on a local computer. Addresses starting with 10 dot. These are used for local communications within a private network. Addresses starting with 192.168. These are also used for location communications within a private network. Many businesses have both an internal and an external address string. Let me explain that. What goes on inside a company's corporate network is not subject to any rules imposed by any external internet service provider. Instead, they rely on their own IT staff to manage and maintain their internal network. The IT manager might set up their internal network based on the 10 dot network schema, for example. They might say that their router is at 10.0.0.1. and that their switches might be at 10.0.0.2 and .3 and .4 if there were 3 of them. They might have a printer at 10.0.0.5 and etc. Because this network is private, the IT staff will decide what's the best method for assigning network addresses to the devices and computers on it. However, the network might also have a web server, and the company might want to expose that server and its websites to the internet. Now they can't just pick any address to expose it on. They have to negotiate with an external internet service provider who will assign the address that they must use. This provider might say something like, your external IP address is at 173.201.146.1, so the IT staff sets up their web server to function at that address. So where do these external IP addresses come from? The Internet Assigned Numbers Authority, or IANA, is the entity that oversees global IP address allocations, among other things. IANA is a department operated by the Internet Corporation for Assigned Names and Numbers, also known as ICANN. ICANN is a non-profit private organization headquartered in Los Angeles, California, that was created in 1998 to oversee a number of Internet-related tasks previously performed directly on behalf of the U.S. government by other organizations. It is ultimately ICANN that's responsible for maintaining the IP addressing schema. In fact, ICANN's primary principles of operation have been described as helping preserve the operational stability of the Internet, to promote competition, to achieve broad representation of the global Internet community, and to develop policies appropriate to its mission through bottom-up, consensus-based processes. So now your company has one or more external IP addresses assigned to them ultimately by an agent of ICANN. Of course, you don't want your business card and your advertising to say something like, visit us at 173.201.146.1. Instead, you want to say something like, visit us at mycompany.com. That's much easier to remember and say. So, how do you assign a name to an IP address so that whenever somebody types in mycompany.com into the browser, that it will come to your specific IP address? This is done by a process called Domain Name Service, or DNS. DNS is really just an index. It translates those friendly names, such as mycompany.com, by looking it up in an index, very much like a phone book, and sending the traffic to the IP address that it has on record. The U.S. Department of Commerce created a governing body in 1993 called INTERNIC, or the Internet Network Information Center, which later was reorganized under ICANN. Registering a domain name is done through any number of for-profit companies, but ultimately these companies must be accredited by ICANN. You can find a complete list of accredited domain registrars in ICANN's website. As we discussed, your computer is known on the network by its IP address. Other devices and PCs on the network will find you based on this address. So does that mean the IP address is always the same? Well, it depends. Computers and other network-enabled devices can have a static or unchanging IP address, or can be given a new IP address every time they connect to the network. In the first case, a network administrator will assign a computer or device a specific IP address, and that address will not change. The device will always be at that specific address. In the second case, a server on the network, often called a domain controller, will hand out an IP address to the devices each time they log onto the network. This is called Dynamic Host Configuration Protocol, or DHCP, which is a network protocol that enables a server to automatically assign an IP address to a computer from a defined range of numbers or a scope configured for a given network. The important point here is that some devices on the network should have a network address that does not change. Think of a web server that has to be at a given address every time someone tries to visit a website. It should thus have a static IP address. Compare that with a typical user's computer. As long as they can get on the network every time they log in, it doesn't matter what their IP address is from session to session. They can use dynamic addressing, or DHCP. Many network devices, including building automation devices, can be configured with a static or a dynamic IP address. Let's revisit and explain one more thing about private subnets. As we said, there are 3 IP network addresses reserved for private networks. The addresses are 10.0.0.0, 172.16.0.0, and 192.168.0.0. They can be used by anyone setting up internal networks, such as a lab or home LAN or anything behind a NAT or proxy server or router. It's always safe to use these because routers on the internet will never forward packets coming from these addresses. Subnetting an IP network can be done for a variety of reasons, including organization, use of different physical media such as Ethernet, FDDI, or WAN, preservation of address space, and security. The most common reason is to control network traffic. In an Ethernet network, all nodes on a segment see all the packets transmitted by all other nodes on that segment. Performance can be adversely affected under heavy traffic loads due to collisions and the resulting retransmissions. A router is used to connect IP networks to minimize the amount of traffic each segment must receive. Remember when we talked about the fact that IP addresses have part of the address for the network and part of it for the node or the device. So how does the device know which one it is? Applying a subnet mask to an IP address allows you to identify the network and the node parts of the address. Default subnet masks are, for Class A, 255.0.0.0, Class B is 255.255.0.0, and then class C is 255.255.255.0. So by reading the subnet mask, a device knows which part of the address refers to the network and which part refers to the individual device itself. Each device that is network aware will have some kind of configuration screen somewhere that allows you to set its IP address and the rest of its network settings. For example, here on the left is an example of a Windows 7 based computer, and on the right is a Linkspring Genesis building automation controller. So how do you examine your network? Well, there are a few commands that you can use that will help you out a lot. Let's start with ping. Ping is used to check for a response from another computer on the network. It can tell you a great deal of information about the status of the network and the computers you're trying to communicate with. To use ping, start a command prompt and type the word ping, followed by the name of the resource you're trying to reach. In this example, we started by pinging google.com. The response tells you that you can indeed reach Google on this network. Notice that we use the name google.com in this example, demonstrating that you can ping a network resource by its name if you know it. The ping response will even tell you the IP address it used to reach the resource. In the second example, we pinged a fictitious computer that we knew didn't really exist on the network just for demonstration purposes, and we said we were going to ping no computer online. The ping command noticed right away that it could not find this computer, and it told us so. In the third example, we pinged a computer by its IP address. The ping command found the network resource and returned a response, demonstrating that you can ping either by name or by IP address if you know them. The time to live, or TTL field, can be interesting. The main purpose is so that a packet doesn't live forever on the network and eventually die when it seems to be lost. It can be an indication of the round-trip time to get a packet to the remote host and back. The reply is measured in milliseconds. In general, it's best if the round-trip times are under 200 milliseconds. The time it takes a packet to reach its destination is called latency. And if you see a large variance in the round-trip times, we call this jitter, then you're going to see some poor performance on the network host. When setting up a device on the network, for example, a building automation controller, you can often save yourself some headaches by pinging another resource on the network. The fact that that other resource responds is a clear indication that you are indeed on the network and can communicate with other devices. And it even gives you a sense of how clean the network traffic is, that is, how fast and how consistently other devices can respond. This information can be a huge first step in configuring any device to work properly using a network. Another very useful command is ipconfig. This command displays all the current TCP/IP network configuration values and refreshes DHCP and DNS settings. Used without parameters, just ipconfig, displays the IP address, subnet mask, and default gateway for all the adapters as we're showing in this example. We can see that my computer's wireless adapter is disconnected, which is correct because I'm using a laptop computer that has a wireless switch and that switch is turned off. My Ethernet adapter is the wired NIC on my system, and you can see that I'm on the linkspring.local domain. My IP address is 10.2.1.145. My subnet mask is 255.255.254.0, and my default gateway is 10.2.1.2. The default gateway is my network's router, which connects me to the internet. There are a couple of other network services that are disconnected, but those are not relevant to our discussion here. If you type ipconfig/all, you're asking the system to give you an in-depth report of much more information. Here you can see lots of information. Some of the more relevant items are the host name, the name of my computer on the network. In this case, it's links10063. Primary DNS suffix, the network my computer is on. In this case, it's linkspring.local. My wireless card manufacturer and model, whether or not I'm using DHCP, or if I have a static address. Remember, in DHCP, I might get a different IP address next time I log onto the system. The subnet mask I'm using, how long I've been connected, and much more information than that. This presentation may not turn you into a network guru, but if you're troubleshooting the system, the network administrator or help desk might ask you for some information, such as, are you using DHCP? What's your computer's name? Is your network card working? By using ping and ipconfig, you can give them the answers that they need in order to help you troubleshoot your problem. Let's talk about a specific example of how a building controller can be added to and configured on a network. For this example, we use a Linkspring Genesis controller. The Genesis controller, we sometimes call them Jennies, has built-in networking capabilities. Once you've connected to the Jenny and configured it, It can work seamlessly on your network like any other network-enabled device. As we discussed, in order to communicate with any network device, you must first figure out what its IP address is. In the case of the Jenny controller, it comes from the factory with a pre-configured IP address. That address is 192.168.1.12 something. To find out what that last number is, first take the cover off the Jenny and find the serial number. The serial number in this example is 1404. So, the last number of that serial number is the last number of your IP address. In this case, the last number is 4, so the IP address of your Jenny is 192.168.1.124. Chances are that your company network is not on the 192.168 subnet, although it is possible. So what we want to do is change the Jenny's network settings from 192.168 to an address that will work with our network. In order to do this, we first have to access the Jenny so we can get to its network settings screen and then change the Jenny to our network's address space. To do this, we have to temporarily change our PC's network to match the network that was pre-configured from the factory, that is the 192.168 network. Once we've configured the Jenny, then we can change our PC back to its original settings, and we'll find that the Jenny is at the address that we set it to. Talk to your network administrator to find out what address on the network you should set your Jenny to. So, we said the first step is to connect our PC to the Jenny at the 192.168 network. To do this, plug an Ethernet LAN cable into LAN 1, which is the LAN port on the right side. Incidentally, there are 2 LAN ports on every Jenny, allowing it to talk to 2 different networks at once. On your computer, you must change the network, we're going to do this only temporarily, to the same network that the Jenny is on. In Windows, you'll visit the IPv4 settings. I'll demonstrate how to do it on Windows 7, but the steps are similar in other versions of Windows. Go to your Network and Sharing Center on your PC and choose Change Adapter Settings. A dialog box will appear. This dialog lists all of your adapters and connections. Find your local area connection and right-click it, and then choose Properties. Another dialog box will appear. In this one, choose the Internet Protocol version 4 option and click the Properties button. One more dialog box appears showing the IPv4 properties. You must set your computer to be on the same network as the Jenny. If there are any existing IP settings here, write them down so you can return your PC to its original settings in just a moment. In our example, we're going to temporarily set our PC to the address 192.168.1.10. Remember, we're trying to get on the same subnet as the Jenny so we can talk to it. However, don't be confused and try to set your PC to .124. The Jenny is already at the 124 address. So as long as you set your PC to an address, any address, on the 192.168.1 subnet, it will be on the same network as the Jenny, and that's our goal here. We chose .10 for this example, but if you're uncertain, you can always check with your network administrator and ask for help. Click OK and close all the windows. Now your PC is on the 192.168.1 network. In fact, it's at 192.168.1.10, and the Jenny is at 192.168.1.124. Let's access it. Now let's see if we're on the same network and if we can communicate with the Jenny controller. So what command do we use for that? Ping, of course. Here we've typed ping 192.168.1.124, which we know to be the address of the Jenny controller. Just like when we pinged Google earlier, we find out that the Jenny controller responds to our ping. Now we need to log on to the Jenny and change its network address to one on our network. Then we'll be able to change our PC back to its original settings and we can hit it there. To do this, you use ProBuilder. Start your copy of ProBuilder and then click File, Open, Open Platform. The platform we want to use at this time is the Jenny, which is at 192.168.1.124, so choose IP and type in that address. The factory default username is Tritium, and the password is Niagara, both in lowercase. Once the connection's been initiated, you'll be taken to the Platform Tools view. This is the starting point for viewing and setting platform-level functionality, including the TCP/IP settings of the controller. Double-click on the TCP/IP configuration. Here we can see how the Jenny controller is set up from the factory. Notice that it defaults to a gateway of 192.168.1.1, and as we discussed, the Jenny controller has 2 LAN ports. On this screen they're referred to as Interface 1 and Interface 2. Remember, your PC is plugged into Interface 1, and we can see that it's both enabled and its IP address is set to 192.168.1.124. Our goal is to change these settings so that the Jenny will work on our network. For this example, assume that our network is in the 10.2.1. something range. Talk to your network administrator and find out if you want the Jenny to have a static or dynamic IP address. If it's to be a dynamic address, click the Enabled box next to the DHCP v4 option. If you want to provide a static IP, make sure this box is unchecked and then set its network settings. For our example, let's say we've worked with our network administrator and we've determined that the Jenny should appear at 10.2.1.137. The administrator also told us that the gateway is 10.2.1.2, so we'll set that setting too. If there are any other settings, such as a domain or some IPv6 settings, we can set them here too. Just a word about the second LAN port or interface 2. A second Ethernet port is available on the Genesis controller. Common uses for this include communication between two isolated controllers over the FOX protocol, or when using BACnet over the IP protocol. In short, you can use one of the ports for communicating on the business network, as we have done with interface 1, and the other to communicate on another network, such as a BACnet IP network. Once you change the IP settings to the preferred address, click Save, and the controller will reboot. You should now revisit the Network and Sharing Center on your own PC and reset your settings to what they were before you changed them. Remember, you wrote them down. Now your computer is back on the business network as it was, and so too is the Jenny controller. Test it out by pinging it at 10.2.1.137. Your Jenny's on the network and ready to go. Just one more word about networking with the Jenny. The Genesis controller has the capability to communicate with several separate network protocols at the same time. The hardware scan service found in the Platform Services toolset shows the myriad of network options available. This view is particularly helpful to integrators as it shows the physical location and the network assignment of each port. The Jenny has option cards that you can plug in and configure for even more network options. If you install any additional cards, the screen will show them to you and indicate how they are configured. Each card comes with its own set of instructions, but the concepts are very similar to what you've seen here. This presentation has shown you a little bit about computer networking as it relates to building automation systems, including network types, categories, and architecture. We've discussed protocols and the equipment used on networks, how important IP addresses are, and even demonstrated some tools to help you check out your network and to configure a sample building automation controller. LinkSpring provides some other videos about various building automation networks, such as how to configure a BACnet or a LAN network. We also provide videos and online presentations about other Niagara-related topics. If you'd like to see some of those videos or would like to talk to a business development manager, please contact LinkSpring at www.linkspring.com. Notice we didn't have to say at 172.201.146.1, thanks DNS, or at 816-347-3500. Thank you for participating in this presentation.